saw from my last stream I did in this room was that you couldn't hear me on the stream, which is a little bit like mind-blowing to me, because I think I'm pretty loud, like within the room. For the size of the room, right? Okay. So if I'm yelling at you, it's because I'm responding to YouTube.
I noticed on some of the earlier recordings, like your typing is louder than your voice.
Yes, I do know that happens. Okay, so that works. Let me check one thing here. I think I might. Okay, I think I know what it is. So I think that should fix it. My claim here is that somehow OBS defaulted to the laptop mic instead of the camera mic, because the camera mic is awesome. Okay, so we are here. I have no idea what day it is, but it's CSE598 and it is office hours. We're talking about dynamic allocator misuse, specifically the T-cache, which is kind of the caching layer that sits in front of the more fun heap parts. Now, I don't know where people are, and everyone just kind of showed up to see what I was going to ramble about. So, let's take a quick look here. Now, one of the things that I think is worth noting if you are watching the scoreboard is there are more people that have finished this module than the scoreboard would indicate, because there are people that have solved stuff ahead of time. So it's not necessarily that people are stuck, at whatever level that is.
That would be 16 then.
16 is a fair level to get stuck on, right? Now, 16 is interesting. In fact, 16 through 20, all of these say revisit a prior challenge now with T-cache safe linking. These literally are one of the earlier challenges, except now safe linking is enabled. Now, they aren't necessarily presented in order of difficulty. Like if I remember right, 16 is actually the hardest of them, right? But that's because I picked like level 9 or whatever level it was, right? And just went in the same order that it was presented earlier. Okay. But safe linking as a concept is just something that people tend to struggle with. So let's take a look at that. Let's see if I can type today. Oh, I have a couple unrelated things that are worth rambling about. You know what I did? I looked into that Jeff bug.
Oh.
I was hoping that you guys would, right? It's open source. You can go there. Right? So yeah, we're gonna detour here. All right? We're gonna detour super early. GitHub.com. Hugsy Jeff. I found what the issue was. I even made a pull request.
Nice.
Yes. Unfortunately, it's not going to get merged in, but I did, in fact, identify a way to fix it. It's not the way that is likely how they want to fix it, which is fine. The interesting kind of nugget here is if I have pwn tools and then I say gdb debug, say bin cat. What this is doing is under the hood here, aside from splitting the windows and doing that magic, is it's spinning up a GDB server that's running my target process. It is then in my second window using GDB's remote capability to attach over the network to localhost on some port. Right? Now, Jeff actually has a built-in command called, if I remember right, Jeff remote. And that's because Jeff tracks some more stuff than normal GDB does. And so they want to have their own command for connecting. But there's no way to instruct pwn tools to do this. right? And so there's a couple different ways that it could be solved. You can look at the PR or the fork that's sitting on my GitHub right now if you're interested in how I decided to tackle it. But what ends up happening here is there is a temp file. I'm going to guess it's this one. I guessed correctly. Because they're using this remote functionality, it assumes, we have to assume that this could be on a remote box, right? Because GDB does have the capability to debug something that's on a remote box. It's what the kind of remote functionality is intended for, or definitely an intended use case. And so we can look here, and what we have is it has a local file that represents that mapping. And that in the current main branch, that file is not getting updated when the mappings change. All right. My approach for the PR was to hook GDB and then update this file, because that was what they were using as the primary means of tracking it. And I was like, okay, whatever. We'll make it so that this file updates. But instead, what they want to do is refresh it so that it will use the info proc maps, or what is it? Proc info maps? Mappings, which I have to continue, so I'm not at the breakpoint. So the loader is ran, where info proc mappings does show the real data, right? And so they're going to source this instead of refreshing that temp file, right? It does the same thing. They have a, what's the word I'm looking for? Branch. They have a branch that does have this fixed. It just hasn't been merged into main. So whenever that does get merged in, I'll update it and get that live on the dojo.
So for the update, do they just copy from POG the PID maps?
So Jeff has a number of ways it can obtain data for like a bunch of different things, right? And so the way that it will work, it will try and use the approach of getting information that provides the most amount of detail. And then if that fails, then it's like, okay, we go to the next approach. Then we go to the next approach. And so one of the things that they changed in their branch that I believe they're going to merge in is they changed the order. Like, should we try proc info maps or mappings before this temp file? And they said yes, where the current main branch checks this temp file before doing proc info mappings, right? And so I didn't want to reprioritize the order that they're doing things. I was just like, okay, well, the thing that they're doing first, let's make it work, right? Where their answer is, well, let's change the priority there as far as what technique they use. Like, it's all valid, right? It all gets the same thing done. It's just a matter of how they want to approach that. So I did look into that. That's what's up. And hopefully that gets merged in at some time in the near future. But it's a fine example of why it's important to know more than just how to use a tool, right? How does a tool work? Question from Twitch here. Does it also bug out when you attach with GDB attach in the Python script? The answer, it's a good question, and the answer is no, which is a good thing to show, which somebody else did point out to me. So if instead of doing GDB debug here, I do like P equals process of this guy, and then I do GDB attach P, and we can continue on. Right now we're before the loader. No, we aren't. I'm a liar. GDB attach, that's because GDB server breaks before the loader, but GDB attach, you've already started the process, so it's already running. That was a brain fart on my side, that's right. But we see here that it is working. We see libc here if we do process and then attach. And that's because when we do GDB attach P, this is attaching locally to the running PID. Like, it doesn't make sense to attach to something on another box. If I'm attaching to a process, it is on my local box. And so that avoids the whole kind of mess of well, how are we dealing with remote communication, right? And then Jeff's remote versus GDB's built-in remote functionality. So interesting little tangent to go down.
I think the other difference is that attach at like main, or like GDB debug like starts at like star I.
Right. No. So that is because you're correct that is a difference. The reason for that difference is if I do the statement was that they break at different points for Twitch there. If I do this, and then we ps aux grep GDB, we see that there is this GDB server running, right? And so the GDB instance that is truly kind of doing the debugging is this server binary, and it's serving over localhost. And GDB server, when it starts something, it knows, like, you only run GDB server if something remotely is going to connect. And so GDB server says, hey, we don't know what's going on yet, right? No remote person has told me what commands to run or what we're supposed to do. And so GDB server breaks, as you mentioned, before the loader. At like the very first instruction. Just like, I think you said start I? Yeah. That's the equivalent of doing start I, where if I do p process and then GDB attach, cat is immediately running as soon as I run this line, right? And so cat right there, by the time I attach, it's just blocking waiting on input. That's why I'm using cat and not like ls, because ls would already be done by the time I tried to attach. And we'll run into a similar thing in the next module with Jeff, I believe. Actually, no. I think I was looking at it and it does. I don't remember. It may or may not work. There's another kind of interesting behavior with Jeff and how they deal with the heap on multi-threaded things, which doesn't impact this module, but will impact the next module. I haven't seen what their current implementation is. And so maybe we all get to experience pwn debug, right? Which is perfectly fine. They're both great tools. Okay, so that was an interesting tangent. I kind of want to say, if we run into something like this again, and one of you guys fix it, like, I'll give some extra credit, right? like you submit a PR and legitimately contribute to an open source project like that, like, that's got to be worth something.
That sounds only feasible during like spring break.
I did it like in like 3 hours, and it's not like I know Jeff's code, right? I just looked at it and reasoned and danced around in it. So one of the things that was helpful here, if you were unaware, GDB has a Python API, right? Just like its own Python API. And so the way Jeff and these plugins work is they use GDB's Python API, which you can look up and see how that works. It's just a wrapper around GDB's implementation. And GDB allows you to execute Python with the Python command. So kind of the trick for me making sense of all this code I don't understand is I go here at a GDB prompt. We need to run something, so cool. I go Python, import, IPython, embed. All of a sudden, I have an IPython shell that has the context of everything that's in the Jeff plugin. So that means that there is this like Jeff object. And then I go and find what is this Jeff thing in their source code. Okay, I understand how this class looks like. I think I want to look at, I don't know, the session. Oh, hey, here's this session thing, right? What does this session thing look like? Well, let's print it out. Okay, I get a little bit of information about it, right? And so I just do this back and forth, looking at the pieces of code that were interesting to me. It's a simpler version of reverse engineering, right? We have the source. Yeah, you can totally do this. I found the parts that were relevant to me and danced around in it until I found something. I'm like, well, this doesn't quite add up. So I don't think it's a spring break extravaganza. I think you guys are fully capable of doing so if you were properly motivated. Okay. Any questions about that as a random aside? No. Got something from Twitch here. Can you debug yourself with QEMU? I never pronounced that right. I've interacted with that project for years and I get it wrong every time. But can you debug yourself with QEMU or something and out what fails when typing VMAP? So it's not that something actually fails, right? That's one of the interesting kind of parts about that behavior is it wasn't a crash. It wasn't a crashing behavior. It was a logic bug in the program itself. The code was doing what it was supposed to do, but the programmer had a misunderstanding about the state of things and how they were kind of deriving data. And so some type of dynamic analysis was definitely helpful there. Okay, so I am back to good old do.c, except I have fixed this code a little bit so that I've learned the error of earlier this week. Instead of having 1, 2, 3, 4, 5, we now use words. So now we know what we're doing. The format is action slot size, so it is consistent, where it was not before apparently. And it doesn't print out nearly as much garbage, so that's nice. So what we were looking at was something that was built like this. So I have no PIE, I have no railroad, I have no stack protector, right? I'm just eliminating everything. And so if we run this, this also does not have safe linking. Yes. It's an out5. Look at this. We can malloc in slot 1 something of 64 bytes. We can malloc something in slot 2 of 64 bytes. We can free slot 2. We can free slot 1. We can go into GDB and we can say heap bins tcache, and we get this nice little printout here. We've seen this, right? And we've also seen this is the chunk that is at the head of the tcache. And if I examine, we'll say 4 giant hacks at, and I'm going to go, 16 bytes behind, right? This would be my previous size. This is my size. We know that the flag values are stored in the least significant bits of the size number. This right here is our next pointer. This is a pointer to the tcache per thread dropped, right? That was kind of the big takeaway from class, which, okay, let's reason about what we're looking at. And it's worth noting that our next pointer here looks like the address of the next allocation. So everything makes sense. Now, starting with level 16, that is not the case. What did I call this other thing? It's not. Build safe. Let's bring this up to the top. Rob's demo patch notes, improved UX. Yeah, kind of. All right, so this is, that does not show on the stream. Make this match up with my head, and let's hide my head. Why is my head, whatever, Twitch problems. Not going to go down the rabbit hole. Cat, build safe. What we see here is I'm doing the same thing. Well, no, let's edit build safe because we'll do it this way. So we're still doing no PIE, we're still doing no railroad, no stack protector. I'm disabling everything because I don't care about these difficulties, right? Now, what I'm doing right below here is running a command called patch-elf. What I'm doing here is I'm taking the elf file and updating the path for the loader and the path for libc. This is why for 16 through 20, unless you understand how this works, do not pull the challenges off the dojo, because you will not have the same version of libc and your behavior will be different. And this is true for a number of challenges in future modules as well, where we're using a specific version of libc. What you will see on those challenges when you ls the challenge directory, I'm on level 1, so you won't see it here, but there will be a lib folder, right? And so it should be pretty clear if I'm using a custom libc in the challenges or not. Okay. Now, why does that matter? Because if we build safe, and then we go and do the same thing, gdb, a.out, we run it, we're going to malloc in slot 1, 64, we're going to malloc in slot 2, 64. I need to remember to script this. Free 1, free 2, control C. Somebody comments 235 is actually the default in Ubuntu 22.04. There may not be changes. However, I am not going to be the one to debug it. So if you pull it off the dojo, it's not my problem. Right? Let me put it a bit more frankly for Twitch. All right. And we go back to heap bins tcache. And this still looks pretty normal, right? Like, Robert, you're saying this is going to be hard. Like, the heck are you talking about? Well, this didn't used to be the case. If you watch, I don't know if it's available anymore, but the live streams that I did in the past, depending on what tool I used and the state of it, this tool, Jeff, is being too smart for us. So if I examine, I do the same thing for giant hex. I go 16 behind. What do we see? Okay, let's reason about it. We've got a previous size of 0, same thing. We've got a size of 5.1, same thing. We have our next pointer, 405 EC5. Is that the same value that we had right here? No. Why is it different?
It got XORed with some stuff.
It got XORed with some stuff. That is right. And so the impact of this is right now I have that double free. Or not double free. Use after free. Right? And so I could print this chunk and I would get these bytes. In levels 1 through 15, you used that. Right? I could print that and get a pointer, or I could overwrite that and write a new pointer. But now I can't just write a raw address there. It won't work. The other thing that's changed is this guy right here. This is our key value. The key value used to be a pointer to the tcache per thread struct. Now it's a whole bunch of random bytes. So that doesn't provide us any context either. This is safe linking, is what we're seeing here. Safe linking, as was mentioned, is a way of kind of mangling these values that are used by the heap to reduce their usefulness to an attacker in the event the programmer makes a mistake. So remember, these heap exploits rely on there being some type of logic bug in the program to begin with, right? If the userland program nulls out the pointers, doesn't allow for overlapping allocations, like uses the heap as intended by the designers of the heap is secure. Right? There's no buffer overflows. We don't have any of these type of problems that exist in userland. The heap is actually totally solid and reasonable. And so from the heap implementer's perspective, they are hesitant to add a whole bunch of security mechanisms because they kind of are like, hey, it's your fault, you're doing it wrong, right? You're using it wrong. So how can we make sense of this safe linking? Well, I have a video, right? And we could watch that, and that would be cool. But I'm pretty sure you can do that on your own time. So instead, what do we know about safe linking? Has anyone watched the video? We know there's XORing. What is being XORed? This is kind of the big miss. Someone says do it live. Oh, we're going to do some stuff live, right? It's a question of what comes out the other side. So this is, in my opinion, the kind of the biggest miss in that lecture, pre-recorded lecture, is people know their stuff being XOR'd and they can like copy pasta whatever Python function I wrote, but they don't necessarily get what is occurring here. Now I show in the video, and I actually don't know. I'm going to see if I can grab the link from the slides because I don't know the keyword that I want to search here, or the symbol.
If you click on the slide like picture, it should advance as well.
Ooh, we truly live in an age of wonders. This probably points to the wrong spot now, but sweet, it doesn't. So this is safe linking right here, protect pointer. And the problem is there's two things, pause and putter. And people don't necessarily get what are pause and putter. Where do these things come from? Well, putter is the pointer. That is the correct original value for the next pointer. Pause is short for position. That is the address where that pointer is located. So, if I go over here, hopefully I'm not cutting myself off, and we just pull off a nice IPython. What are we doing? We're taking the position and we're bit shifting it by 12 bits. Why 12 bits? Is this just an arbitrary number? 12? 12 is a good number. There is a reason. I can't hear you, sir.
I don't know. Does it make it like a page offset or something like that?
Okay, so 12 bits does get us to a page, right? Because hex 1000 is a page. And what do we know about the bytes that exist for the page? On like a reasonably sane program that doesn't have no PIE. So this is the first 12 bits. Now let's look at like libc. Libc will still behave because libc is not impacted by no PIE. So we're talking about these bytes right here. What is kind of unique about these earlier bytes? These are the ASLR bytes. These are different every time the program is ran. Now, what do we know about these first 3 bytes? Or not 3 bytes, 3 nibbles. They are not unique for every time the program is ran. And so what's happening here is we're shifting away the constant nibbles, right? The offset into the page. And so that means the least significant bytes here of this bit shifted value are going to be the random ASLR bytes, because we want to introduce randomness into what we're doing. Pull that back up here. So we say our position is hex 405 B10. Then we have our pointer is hex 405 EC5. All right. Let's go back here and look at libc. The position gets bit shifted by 12. I don't have a good word for this bit shifted thing. Does someone have a preferred word here?
Shifted pause. I don't know.
Shifted pause. And so it was. And so now we have shifted pause. Shifted pause gets XOR'd with the pointer. All right, we can do that. Shifted pause, XOR'd pointer. Obviously, we want it in hex. Is that that? It's not. Why? I made a mistake in my Python code. There's only like 4 lines and I made a mistake.
Can we show it that way?
No. What is pointer?
Oh.
Pointer is the actual next pointer. It is not the XORed thing. So let's look at what that actually is. The actual next pointer should be AC0. Wait a minute. We somehow went and did the same thing, but we went the other way. Like, what happened here, right? XOR is a reversible operation. And so in simple cases, and this is a very simple case, this is why we don't have PIE and the bytes, or the nibbles, I guess, because it's 1.5 bytes. These nibbles here are the same between position and pointer and our mangled value. And so in the simple case, yeah, we can just XOR this one way and XOR it back and everything works out. But you'll find in these challenges, that is not the case. So let's just prove we can do the same thing and get the mangled value. Let's set the pointer to be the correct thing, 405 AC0. And then I want to say hex of shifted pos, XORed with the correct value of what the next pointer is. And we see now I do get that mangled value. Right? And so that seems really easy, Robert. Like, what are you going on about? Well, let's look at a little bit more complicated case. We need to look at build safe. Let's make a real program, right? Let's not have these training wheels on. Okay, what do I need to do? I need to not segfault. That's what I need to do. How did I manage to do that? Oh, I commented out. Yeah, that would be problematic. Okay.
You want like the regular GCC?
So I'll show what I was grumbling about. Oh, you are right. So one of the things I had commented out the interpreter and libc are closely related. And so having one but not the other will make things not happy. You are correct here, though. I do want the regular libc. So good catch there. And we still don't segfault, as it should be. All right. We're going to malloc in slot 1, 64 bytes. We're going to malloc in slot 2, 64 bytes. We're going to free 1. We're going to free 2. We're going to control C. We're going to say, Jeff, show me that heap. Okay. So this is still very similar, right? RF training wheels. Yeah, this is where it all goes off the rails. And the only difference here now is that our addresses are significantly larger. So let's see if we can do that same thing. This is easy, Robert. What are you going on about? We have let's cheat with Jeff here and see if we can get the random value. That's my pointer. I'm going to do it the correct way this time. We have a position, and our position is going to be, I need to examine for giant hex at this chunk. And I'm doing this so that you can see it. The position on this T-cache, because it's a linked list, the position is the address of the allocation. right? It's this B10. And the pointer that is there is the address of the next allocation on the linked list.
Which is the head, right?
So head itself in our little GDB printout here. Oh, I love it when I can use a whiteboard. I don't think you'll be able to see it. Like a whiteboard is like the single best investment I have ever made in my life. And one of the worst days of my life is when I threw out my whiteboard when I moved. I used to have a giant home whiteboard. So remember Jan's amazing diagram where we have, it's not size, it's count. And then we have, I don't know, I'm going to call them buckets. Right? I don't really care. And these are the head pointers, right? And so this, well, it wouldn't be that one, it'd be like one of these. This guy here is the head pointer for 64-byte allocation, right? He's going to point somewhere. He's going to point to BB10. I don't know if you can see it or not. There we go. This is where that next pointer is. Right? Where does that next pointer point? If it was not mangled.
To the next thing.
It's going to point to the next chunk, right? He's going to go wherever, whatever was the previous head of the T cache, which according to Jeff here is BAC0. OX BAC0. And then this is another next pointer that currently points to no one. That is an amazing diagram that looks great for you and looks ridiculous for Twitch. But
That's not the worst.
yeah, I've definitely done better. I think the camera's just too close. But anyways, so we don't really think about head here, right? What we're looking at is this value of the first chunk, the address of the first, not chunk, the address of the first allocation. And I'm using the word allocation because the beginning of the chunk is actually 8 bytes behind the beginning of the allocation, or 16, depending on how you think about it. Where the address of the allocation is the beginning of the user writable memory, and that's where the next pointer is. And so the address of the allocation is the position. The next pointer that is in that freed spot is the pointer that points to the next head. Those are the two values, position and pointer. Now, that's it. What libc is doing, all right, what the heap is doing, is it's taking the position and then the location of the next allocation and doing that bit shift by 12 and XOR. So let's see if we can do the same thing here. We have our position, which was BAC0 should be this guy here, B10. And so I didn't really need to do this X giant hex is the kind of the takeaway here with this ridiculous drawing. If I can just see this right here, I know this is my position, and then this is my pointer. Because this value is what was the next pointer that was chilling at this spot. We're going forward here. We aren't going backwards yet. Looking at faces. Making sense? Kinda? Kinda? All right. If not, like, it's cool. We can sit here for 20 minutes and do it. All right. So there's my position. I should be able to take my position, bit shifted by 12. I should XOR it by my pointer. I should be able to hex it. Ah. Something bad happened here. I didn't add enough zeros? Someone's starting to like this live demo. You just want to see the clown fiesta. So all of a sudden, this isn't adding up for me.
What are we trying to get?
But I'm trying to replicate. This isn't that hard. This isn't rocket science. We see right here what the heap is doing. It takes the position, it bit shifts it by 12, and then it XORs it by the pointer.
Yes.
Okay? I'm trying to do this exact same operation and come out with the exact same answer the heap did. Something doesn't add up.
Wait, I thought we did get the same answer.
We did get the same answer the heap did, and I am illiterate. That's okay. That's why you're here, all right? To catch me when we do it wrong. Now that was pretty cool, right? But this is actually still a pretty simple case, believe it or not. Because the higher order bytes of this are the same between the position and the pointer. Right? If the higher order bytes are the same, then you can do on the pre-recorded lecture, I think I called it demangle. There was this magic like one-off demangle function that I show. And it's something to the effect of, because we got to know, how do I go backwards, right? We saw how the heap does it, goes forward, but how do I go backwards? Well, if I go backwards, what information do I have? I don't have what?
The real pointer.
I don't have the real pointer. So instead, the two things that I get, and this is where the live demo goes off the rails. Because I didn't have time to scribble this out to sanity check it. But I've seen people do this. All right? These are the people that know how like encryption works. That's not me. All right? Don't ever listen to me talk about anything crypto related. Because it's all just magic to me. Okay, so what we have is the mangled value, right? And so, like, the way that they do these things is, what did we call this? No, we don't have a name for mangled. Mangled footer. And that thing is going to be footer XORed with position. Right, you remember doing these things? Is that how you XOR? I don't even remember how you XOR. Circle and a plus. Feels right. You know what? Let's go with Python. We're gonna diamond it. Right? It just feels better. Okay. So we know that, and we have mangled pointer. And so this is a fact where we have the information and we know what it consists of. The other thing that we know is what?
Reversible.
Reversible. Okay, like we know XOR is reversible, right? But this alone isn't enough. I have three variables and one equation. That's not enough for me to reverse. What's the other thing that I know?
Position.
Okay, I know position. So I have position. Right? So this should be enough for us to reverse this. What's the other thing that with all of this, we can do this. We know that the mangled pointer, that's a lie. This gets bit shifted by 12. Bam. It's pretty now. Right? So, if we have position, then we can get the position bit shifted by 12. And what we're solving for is pointer. So we can say pointer should equal, we XOR both sides, mangled pointer, and then we XOR that bad boy by position bit shifted by 12. Right? It's really not that crazy. That should work, right?
Are we using the 3 nipples at the edge?
Well, the bit shift by 12 gets rid of the least significant nibbles.
This seems mathematically possible.
This seems mathematically plausible, right? And so we can do that. In fact, that's kind of what we did here. But what happens if the position and pointer don't have that relationship that I talked about? Well, then things get weird. Let's see what happens then. Now, I don't think you can do this in the challenges. Well, maybe you can. But what I'm going to do is I'm going to malloc. I'm typing 1 now. We've gone too far. It's time to go back to the comfy world of Python. Write a script, make this repeatable because there will be failure. From pwn import star. Okay, p equals process a.out. p.send. I want to malloc in slot 1, 64 bytes. And I want to send line because scanf. I'm now going to malloc a whole page. And let's put that in, I don't care, slot 4. And I'm not really going to do anything with it. Then we malloc 64 bytes in slot 2, just like before. We're going to free 1. We're going to free 2. And then we'll go interactive. Does that seem reasonable? Seems reasonable. Oh yeah, let's use our newfound technology here. All right, we have the tech. We're living in the future. Somebody on Twitch says, is malloc 4, is this a guard? Now, this is something that isn't, the concept of guards or guard allocations isn't something that we explore until the heap 2 module for kind of deeper heap things. But so it is not, it does serve the purpose of a guard. However, this is all in Tcache, so I wouldn't need a guard to begin with. And I'm not using it as a guard in this context, just for the Twitch question. You guys don't need to understand anything that I just said there, right? That'll be something that you'll ask about in 2 weeks. 2 weeks time, maybe a bit over spring break, we'll be like, guards, man, what are they? Okay? Because the heap is deep. All right, so we have our super sweet script here. What did I call this? Demo.py. Once again, cannot type. Okay. Now, if we heap bins Tcache, we have something that looks pretty good. Let me see. Does this have the property that I'm desiring? The answer is no. Did this do? Okay, it didn't like. I need. It's embarrassing. I have to do this. Cool. So if you didn't catch that, one of my mallocs, it didn't like the hexadecimal number I put there. It said invalid value. And so I just changed it to a decimal number to make scanf happy. Heap bins Tcache. Does this have the property that I want? The answer is yes. What is the property that I want? To show how this all blows up and becomes nasty. You said yeah. So what do you think it is that I wanted?
How to describe it? So like anything that's not last digitable are different.
You want all the ASLR bits to not be the same?
Yes, I want some of the ASLR bits to be different, right? And we see that right here, where this starts with 8.7, and this right here starts with 8.6. So it's a difference of just 1. It can't hurt anything, right?
He said with foreboding foresight.
Nah. This is going to work. So, tell me right now, without me doing xgx4 or x/4gx, what is my position and what is my pointer based upon this tcache output? Something 0. 6C0. All right. Which is that? Is that my pointer or my position?
I think your position is 002.
You think, okay, so if I understood correctly, the answer I heard was the position is this value right here, and the pointer is this guy right here ending in 66C0. And that would be correct. So let's get that over here into Python. Here's my 66C0. There is my position. And then what do I do? Well, what does the heap do? Shift position right by 12.
XOR the result with pointer.
XOR the result with pointer. And then we want to look at it as hex. All right, we have a value. Where should this value be located if we did this correctly? At position. Oh, don't hit that button. There's no coming back from that button. I know T-Mux. I know T-Mux well enough that that's a good button, but now is not the time to hit that button. Okay. So should be located right here.
That looks similar.
And that I'm covering myself up. Can I make this? Okay. Okay, you can still see it on Twitch. And that looks, it's the same thing. You're like, Robert, what's wrong? Right? This is all working. Right? You're making it into a big deal, but we're going forward. Now let's try and reason about this backwards. What do I have? I have position, and then I have this mangled guy, right? So I should be able to say, all right, well, position, bit shifted by 12, or not XORed by 12, we bit shifted by 12. We XOR it by the mangled garbage. Looks good.
Wrap it in hex.
Let's wrap it in hex so that we can reason about it.
That looks, yeah.
Huh. Looks pretty easy. Is it the same?
Yes.
Yes, it is. That is not what I was hoping would happen.
Is it because like the bit
Something.
different was like inconsequential in the math or whatever?
It should matter. Like the scary, like I can make a scary example here, right? Oh, that's not GDB. That's IPython. If I have something like RSP, right? Something that's totally different. And for whatever reason, I need to write a next pointer, and I want it to point to something on the stack. Right? That's something you might have done in the earlier challenges. What do I need to do to mangle this and make this work?
So you have the pointer you want. You're going to need the position.
Okay. Well, let's say I want to do it right here. I want to make chunk 2 point to RSP. What do I got to do?
We have to bit shift the 720 address.
Okay.
And then XOR it with the RSP.
We have our position, and then we XOR it with this, and we get this right here. All right? Feels good, feels right.
Okay.
Let's do it. Let's set this right here. Now you could do this via read or whatever, but we're just going to use GDB to make the magic happen. And we can confirm that that is what we wrote. It is what we wrote. That is not what we wrote. So it wrote it as a int. So that means I need to take this, cast it as a long star. Is that what we wrote? There we go. All right.
What happens if we do heap bids Tcache now? We should see it, right?
So is that, we haven't gone anywhere.
Okay.
Right? That worked. So we see how we can mangle our own value and put it there. Not bad. We see how we can demangle things. But what I needed for this to occur is I needed the position value. I needed a heap leak. Right? And we just kind of had this heap leak. I've just been like, whatever, we have GDB, we can print this out. But if everything is mangled, how do I get a heap leak? How do I know where the position is if every position is mangled?
Do you hope you get one that has the ASLR bits aligned? I guess you don't know if they're aligned.
And let's just finish this out and see if we can get malloc to return. Right? This seems like a reasonable thing to try and do. We'll malloc into slot 1, something of 64 bytes. Did I do bad here? Malloc into 2, 64 bytes. Heap bins, Tcache. What is it mad at me for? Oh, we used the technology. I got to type up top. Okay, so we'll continue over here. Well, now we're in the right window. Malloc into 1, 64 bytes. Malloc into 2, 64 bytes. Sag.
Oh yeah, because our stack pointer was ended in 8, not 0.
Where is it here? Yeah. So one of the things that is checked with this new version of libc and the addition of Tcache is that the least significant nibble of every allocation must end in 0. And so we wrote something that was totally cool, right? But we failed because you're not allowed, malloc isn't allowed to return that pointer. So what do you think we would do if I wanted to overwrite RSP? How do I get around this problem?
You can maybe segment it by 8.
Yeah, we could just do the same thing, but start at RSP minus 8. And then assuming that we can write, 16 bytes or whatever, right? We can write 8 plus what I need. We can just start writing behind it and then overflow into it. Totally reasonable. There is no way to return a pointer that doesn't end in 0. There will be challenges here at the end where you're like, I need to return something that doesn't end in 0. That is by design. It is not broken. You will need to be clever. Okay, so let's see, what do we got? Question. I fell behind on you here, Twitch. What do we got? You're going to need a heap leak. Yes, you're the inspiration for the grand heap hunt. And the other comment is getting more than one leak is a real challenge. And I wouldn't say that it's necessarily a challenge, but it is an additional requirement, right? And so Tcache, safe linking doesn't make it impossible. But all of a sudden we've got handcuffs, right? I can't get the pointer I want. I can't turn a heap into a pointer that I want without having a heap leak already. And so a simple programmer mistake in user land now has to be more glaringly wrong, right? I have to be able to take greater advantage of it than what we had before. Okay. Now space is a good button. So if I instead, I actually don't want to do this. What I want to do is grab my demo.py and let's see what's going on. And I just have one malloc. Pretty boring, right? All we did was just called malloc. And we say heap bins tcache. Yeah, it's pretty exciting, Robert. It's good stuff here. And look at the 4 giant hex starting right behind it. What is this garbage right here? This is where the next pointer should be. All right, but if we look at what Jeff says here, well, there is no next thing. All right, and we can vamp. We can vmap. All right, where is this? Well, it's nowhere. But it looks like something, doesn't it? What else does Twitch say here? My issue is understanding how this safe linking works. Yeah, we did safe linking forward, right? The problem is safe linking backwards and what you need, right? I need a position and I need a pointer. But if I have neither, I have nothing. Right? How do I get that initial heap address? Well, this is probably, we're looking at this. What does it look like?
That bit shifted
It looks kind of like this. Yeah, but it was bit shifted by like 12 bits. And then it was written there.
Oh, because next is usually nil, so it XORed it with just zeros.
Yeah. So does that give us some kind of information about the heap? Like if I were to take this and go 0, 0, 0, and then we 0, 0, 0. Hey, it's not immediately a heap address.
But it's in the heap.
But it's pretty easy to turn it into one. And that gives me an idea of these ASLR bytes. All of a sudden, I have something that isn't necessarily position, is it? No, I got 201.0.0.0. It's not position, but it's on a heap. No, 601E00. Yeah, so it's not position, right? But it's contiguous with position. And if I were to take position and I shift it by 12, is it the same thing as what we just saw there?
Yeah.
So had we kind of reduced the mess here? Yes. Did the programmer make a mistake?
No.
If they let us read it, I guess, maybe.
If you malloc free and breed, so it is a use after free.
Yeah.
The programmer didn't null out that pointer again.
Oh.
So from the perspective of the heap, that is your fault, not the heap's fault. And so hopefully you can see how these kind of relate, right? Now, I have to cheat, but it's okay because it's in the video. If we look at this do.py, these two functions here are, I just give them to you. And I say, these are the magic functions that will do things. We have mangle and we have demangle. It's super easy, right? And if you look at them, the first one makes a ton of sense. Mangle. What do? It's literally what we've been writing up here on the board this whole time. That is the forward operation. But what if I only have the next pointer and I don't know where it is? What if I have less information? I just have this heap leak. I don't know if it is where it is. And so the heap leak I have is not XORed with 0. Right? Like, let's say I had, what do I want to do? I want to run, first I want to edit demo.py. To be this, cool. So this is our heap bins tcache. I've got my two allocations. They're slightly different. Robert, this is the thing you said was scary, and it's not scary at all. This is the only thing I have. I don't know where this chunk is, but all I have is this. Is that enough for me to do this? The answer is maybe. In some cases you can, and in some cases you can't. Because we can rewrite this, because if we assume that the pointer bit shifted by 12 is the same as position bit shifted by 12, and this is where that page matters. If all I have is the mangled pointer, then I can derive a relationship between the pointer and the position bit shifted by 12, because they should be the same if they're on the same page. That is what demangle does. Right? We'd have to add like another 4 or 5 lines here of amazing XOR-ness. If you want to do it, we can try and figure it out. I don't know it off the top of my head. Right? But that's why we can say demangle, where all we have is the mangled pointer. This, in order for that demangle to work, we have to have the assumption that the mangled pointer bit shifted by 12 has a relationship with the position. So let's go back to here. Let's is this going to, I don't want any of that. Time for some cool tricks. So I have this Python file that just has 2 functions in it, right? If IPython, you can go -I and then give it some Python file. It will interpret that information. So now I have a demangle function. Now, if I run this demangle function on the magic value that we have here, is this going to work? No, because for whatever reason, I made it not valid code. All right, we'll try again. Just give me a number. This is the number I want. It's a little bit hard to see. What do we see here? FA6C. Oh, we're off by 1. Why are we off by 1?
Always the page.
Something about pages.
Or like the last 0.
Right. So I said that the demangle function works on this assumption that the pointer and the position are on the same page. In this example, they are not. They're off by 1. And because of that, that is the difference here between CFB and CFA. A plus 1 is B. So then when we use this demangle function, our assumption is wrong. And that gets bit shifted by 12, which becomes what gets XORed with the least significant bit. And we end up with an error of 1. Now,
Does that matter?
it,
Because we always want to return a 16 aligned address, right?
Okay.
But if the like difference between.
Oh, the difference like carries over in the next bit or next byte.
More than-
right, yeah. What if the distance between the position address and the pointer address is, I don't know, hex 37 pages? Right? When we, in these kind of T-cache challenges, we are always dealing with small-ish allocations, right? Because that's what T-cache is about. It's about optimizing the small common case. And so this will be true a lot of the time if we're doing these like dinky little small allocations. But what happens if we do some small allocations and I have a program that, I don't know, it decides to alloc 5 pages, and it's going to do some small allocations, it's going to alloc a page, or malloc a page. Now, we have no idea about the relationship between the pointer and the position. And so this kind of one-off demangle function will not work. Instead, you have to use what we have been doing this whole time from the beginning, which is mangling it forward,
Okay.
right? Because if we look at the difference between SL, yes, between mangle and demangle, we make assumptions. We say this is the only thing we got. We can rock and roll. But if the pages are different, then I need to use this mangle function. And I would have to say, well, what if the distance between the address and the value was like 1 page? We could do that, right? Would that work? No, that wouldn't work, because I'd need it to be OX 1000, because this is before the bit shift. That would work. So I have to specify what do I think is the address and what do I think is the pointer. Right? Let's see if we can do that over in our Python code here. So we have our magic guy. Demangle doesn't work. So I probably want to try to mangle. And what happens if I mangle this guy with itself? Well, that's not quite right. Okay. What if I take that and then we bit shifted by 24 and we XOR it with, no, I'm all over the place here. Okay. This isn't like this, so that's just confusing. This is like this. We'd want to say the mid value is going to equal the mangled guy bit shifted by 12 Then we say the mid value XORed with the obfuscated pointer is going to be the new mid value. And all I'm doing is what we have over here. Then we say the mid value bit shifted by 24, XORed with the mid value. Robert, they gave me the thing that was off by 1. All right. We just did demangle, but we did it the long way. So what value is different here between mangle and demangle? Oh, Twitch is going off. Not gonna lie, I'm confused. Yeah, it is confusing. I'm confused too. This is a team effort here. Somebody says they don't remember demangle being in the video. What? And that's because I think it is in the video. If not, freebie. Demangle works, but it relies again on the address of the page of the pointer and the page of the position to be the same. Right? That's why right now we have a delta of 1, and we're seeing our result is off by 1. So clearly, I just need to change like one of these values here in my demangle function. Which one? Did I do it? Did I do it? No, that was bad.
You change like the page value?
That was bad. Right, so one of the values here is the address, right? And so one of these needs to be this is where we got to write it out. Gosh, dang it. This is where it all goes off the rails here. And this is where it gets hard. Twitch? Is Twitch going to save me? Twitch says they think I know which. All right. They think they know which, but it's such a cheap way to demangle, I'd rather get a fresh leak. What if you can't get the leak? Right? The scenario here is I only have this mangled pointer. If I can get the mangled pointer and something else, I'm in pretty good shape, right? If I can get the mangled pointer in the position, then it's really easy, right? We don't need to try and massage this into something that works. But there will be a scenario, maybe not in this module, maybe in this one. I don't remember exactly what you're facing here in 16 through 20. There will be a scenario somewhere in this course where all you have is the mangled pointer and these positions are different. Okay? And what you'll end up with is, oh, it's next module. Next module, I know for sure you ran into this. Now that I'm thinking about it, right? Maybe not this one, but next module you definitely do. What you can do is the heap is deterministic, right? As far as the page. I said, well, what if it does a bunch of small allocations and then it does 5 pages, then it does small allocations, and it does another page, and then it does something else. The delta between the position and pointer will be some constant value. And so you can analyze the state of the heap using GDB or statically if you're insane, right? Because the heap's dynamic, it makes way more sense to me to just break and then look at the distance between 2 pointers, right? But if you want to do the math, you know, have at it. Where you can figure out what the distance is. And then using that value, which I believe I'm just going to leave as an exercise for next week, because I know it's all over next week. So I think I'm getting ahead of myself here. You can use that information in just a mangled pointer to reverse the whole thing. All right. Aside from the magic of turning a mangled pointer into a pointer, where the values are not, or the pages are not the same, does anyone have any questions? That's going to bother me that I can't think of it right now. Twitch says you should first shift right by 12, then -1, then continue with my current function. Okay. Let's see. Let's see what you got, Twitch. A bit shift by 12. And then I -1.
It's like that might be the data that I want, basically.
Right? That does, in fact, if we think about that, that gives me something. Where was my GDB? Do I not have GDB? I don't have GDB. It's a sad day where I don't have a GDB session open. Okay. So, because if I remember right, it was, what did I start with? 4A, was it 8.4, and then is this in GDB? No, I don't even know what I'm looking at. Okay, that's going to attach a GDB session. Let's make this be something like that. Cool. Heap bins tcache. I've got, the only thing I get is my mangled pointer, which would be the giant hex that is located here. Okay. You just say words, Twitch, and then when I try and follow your guess here, you get real quiet. So my mangled pointer is this. Okay. And then my mid needs to be this, bit shifted by 12. And then logically, that would be 6A. Okay. And that is the same as, we're going to figure this out.
That's our position.
That's the same as my position bit shifted by 12.
Yeah.
Okay, so now what I have is the position bit shifted by 12, and I have the mangled pointer. So,
Wait, the mangled pointer is pointing at the position? Or is the position?
this, isn't that, did I copy the wrong thing? I did copy the wrong thing. Yeah, I said mangled pointer equals, and then I did the address. Okay. Mangled pointer is this. Yes? No.
Yeah.
Yes. Okay. Mid. Mangled pointer. Bit shifted by 12. -1. And then I want to look at the hex of this. What do we have? Does that have any relation to anything? Not
Yeah.
immediately. Okay.
Sorry.
So what do you want to XOR it by? This is where those crypto guys, man. All right, they know these things.
XOR with the mangled pointer?
You want to XOR it with the mangled pointer. Okay. Let's see what happens. XOR that with mangled pointer. Does not look like it in it. It's almost a thing.
Almost.
Okay. So then if I take that and I XOR that with, it's going to be one of these two. I'm going to go with mangled pointer, bit shifted by 24. No, it must be mid by 24. Did I produce a number? I almost produced a number. 696A. Okay, no. We had it the first time with the mangled pointer. This guy right here. What is this?
We have everything except the offset bits, correct?
Right.
So now we have our correct. This is shifted to our position.
We
Position.
have our position, except now that we subtracted one, this is all wrong. Thank you, Twitch. Right? Because that should be 55888, CD, 6A, 6, 9. So it's off by 1. Why would that be off by 1? Mangled pointer. I couldn't do mid. So I'm still off by 1 here. Are you guys cool if we just leave this as an exploration for next week? Next week you have to do this. All right. Now that means come Tuesday, I have to do this.
But is this the position? Isn't this the position? Oh no. Yeah, we're wrong.
Yeah. So this would be our position, and then this would be our pointer. 60. Oh wait, what did we? Ooh.
Yeah, we got the position. We got like the next position or something.
So we ended up getting the upper bytes of the pointer. Math is hard, guys.
That is.
Okay. But if we have the upper bytes of the pointer and we know the distance, we could add one and get the position, which would give us this, which would then let us XOR that with this, which would give us this. We could do it.
Yeah.
All right? I promise you. All right. Next week's, I don't know if it's in the pre-recorded videos. I'll have to double check that. But I know that I have written a function that does this, where you just provide your mangled pointer and then you provide an offset, and it will just math it away, right? Because you only have to figure out the math once. Then you write a magic function that just makes it work. And that's not only true for you, but that's true for me. All right. Any other questions? If not, I'm going to let it go and call it there. Twitch, it was fun. We got most of the way there. All right. I see nothing else on Twitch aside from them just being like, I was right the whole time. I appreciate everyone hanging out. If you have questions, ask on the Discord. Goodbye and good luck.